we ever can, even within a regular ACS meeting. So our first speaker today is Mark Johnson from Yale University. Mark received his bachelor's degree at Berkeley, where he did undergraduate research with Brad Moore. He then went on to Stanford, where he received his PhD working with Dick Zare and did a postdoc with Carl Lineberger. So you're starting to hear a list of some of the real physical chemistry greats in experimental PChem. Mark moved to Yale in 1985, and where he's been for his entire academic career. I could probably spend the next 5 minutes going over all of the awards that Mark has received over the years and all of the great things he's done for our community, including being the chair of the physical chemistry division of the ACS several years ago, as well as running a number of Gordon conferences and activities within the APS. He is a fellow of numerous societies, including the American Chemical Society, American Physical Society, AAAS. He's a member of the National Academy of Sciences, as well as the American Academy of Arts and Sciences. And as I said, received numerous awards, including most recently the Langmuir Award from the ACS. And I've known Mark well for a long time. And what I really enjoy about Mark and Mark's work is that he took the really detailed chemical physics types of studies that he learned about from the Moore and the Zare and the Lineberger groups as he was coming up through, and really the combination of that and then developing some just beautiful experiments using multiple lasers, mass specs, all these different complicated things that just kind of make my eyes blow up. And he uses them to explore interactions that are important in determining bulk properties, using clusters that are small and cold enough to really be able to characterize the underlying structure and bonding and be able to ask the types of detailed questions that are needed to gain chemical insights into important phenomena. So today's talk is going to be entitled, Mark likes long titles, it's Deconstructing the Chemical and Spectroscopic Properties of Water One Molecule at a Time, the case for slow and sure in this race to the bottom. So thank you, Mark, for agreeing to give this talk, and I will turn it over to you.
Thanks, Anne. And, Anne and I indeed we joined forces over coffee break in the molecular spectroscopy meeting, and I think 15 years ago, more than that. And it's been, we've been off on one adventure after another ever since, and it's continuing, through the COVID rate, the quarantine era. So we continue to have a very productive collaboration. I thank you for all those nice words, and back at you. All right, so we're going to talk about, this is an unapologetic PChem. It's just a PChem division, okay? And we're going to talk PChem today. So, that's quite a refreshing thing, and I'm very happy about it. Partly because we do a lot of things that are applications, they're practical applications of the kind of tools that we built over the years. And so the apparatus that I'll be talking about today is in use in ongoing experiments in our labs that are ranging from environmental chemistry to catalysis to jet propulsion, ionic liquid propellants, and so on. So these are useful technologies, but we built them to do PChem, and we built them to do the experiments that I'm going to describe today. And so I'm going to talk about water dynamics from the bottom up, and the work that I'll be talking about. I want to get this right up front. The basic water deconstructing the spectral dynamics of water are funded by our NSF program, and I'm also bringing in work that we do to look at how protons, the speciation of protons in water, and that's been funded by the Department of Energy. Okay, so this is what the tool looks like. So we built this thing. We made many false starts over the years, and this is the current incarnation of it. It's a hybrid spectrometer between laser spectroscopy and high-resolution mass spectrometry. And so this laboratory was commissioned 2 years ago, specifically designed for the infrastructure you need for this kind of apparatus, this laboratory for structural mass spectrometry. And just to give one slide of who cares beyond physical chemists that you should have such a thing. And so this is an example where we're using our hybrid spectrometer in order to work on a project related to proteomics, the sequencing of peptides. And so we imagine that if we have the way you usually do this is you get a mass peak and you don't know what it is. And so you break it apart and you see the fragment masses from it. And then you look up a library to see what fragment pattern that would tell you what the parent molecule is. And what we did is add a third dimension. So for each mass, we can cool that ion down so that it will yield a very high resolution infrared spectrum. So we have a new dimension for doing routine chemical analysis. And so we are now deploying one of these instruments in our general use instrument center for the chemical sciences at Yale. And so we're bringing spectroscopy to mass spectrometry, and we do it using cryogenic vibrational predissociation of the ions. Now, we're all indebted to Michio Okumura and YT Lee back in the day when they developed this seemingly simple contribution to JCP in 1986, where you can take a spectrum, an infrared spectrum of an ion. If it's an ion, you can mass select it. And then problem is, of course, you never have enough ions to do traditional absorption spectroscopy. But if it's an ion, you can use an action spectroscopy if you change the mass with the action of a photon. And so one photon comes in and will break off a weakly bound adduct, and you measure the action of the photo fragment and scan your laser. And so it works beautifully. Everybody calls this messenger tagging or just plain tagging spectroscopy. And that's what I'm going to be using when I show you spectra. It's going to be done with this photofragmentation tagging method. I want to talk about water. If you have a water molecule and it's just, isolated in a vacuum, and you ask where do the OH oscillators, what is the frequency of those oscillators, you get two solutions, and those are the cooperative normal modes of coupled stretches, the symmetric and asymmetric stretches of both of those OH groups, and they give very sharp lines, 3,700 wave numbers. We're going to need to remember that number. You just take water and stick it in solution and let it hang out with its own kind, and you reduce the force constant of that frequency by almost a third. And so you get absorptions that are down here at 3,000 wave numbers that are far removed from where water wants to be by itself. And water is very unique in this way. These strong hydrogen bonds in water really torque a water molecule. And you'd like to ask yourself, with this miserable water down here at 3,000, what has happened to it that has caused it to wander so far away from the mothership over here at 3,700, right? We want to know the neighborhood that does that to a water. People have thought about this long before us. And so there's a famous compendium of everything you want to know about water. And so you can draw these diagrams and say that what's controlling the frequencies of the OH stretches has to do with the particulars of its hydrogen bonding environment. And so D is a hydrogen bond donor, A is a hydrogen bond acceptor, and the more donors and acceptors it has, the lower the frequency. Kind of a simple rule that I think is very, it's very appealing. It's like Lewis dot structures. It's kind of a way to get your head in the game of what kind of stuff would cause OH oscillators to change their frequency. Okay, then so we have the local structural environment, the hydrogen bonding environment. That's one of the things controlling the frequencies. The other thing that's special about water is even if you had one frequency associated with a particular structural environment, and you monitored somehow magically that frequency, you would see that as the waters are in liquid water, they're changing the structure of the liquid, is modulating the distance between the oxygen atoms. That modulation is going to strongly affect also what the frequency of that oscillator is. And so you get this idea that thermal fluctuation of the bond distances will give you very dramatic changes in the frequency at which an OH oscillates. So we like to call this spectral diffusion. And it happens in hundreds of picoseconds type timescales. People like Mike Fayer and Andrei Tokmakov have worked this over for the last 20 years of asking yourself, how fast does the frequency sweep through the spectrum? So we have two things that are contributing to give this diffuse, featureless blob that is the vibrational spectrum of liquid water. And now, as a chemical physics person, as Anne said, trained in the knowing of every silly thing you can possibly know about the quantum mechanics of a polyatomic molecule, We do not like lumps when we're in the chemical physics spectroscopy game. So is there anything I can do that would challenge that model, that traditional model? And I would in this talk, I'm going to ask tough questions. I'm going to ask how does the local OH frequency, if I could only isolate one of them or one water molecule, how can I construct an experiment that would reveal how the frequencies specifically depend on that local environment? And if I did grab one of these oscillators, it is implicit in many of these theoretical descriptions of water that if I could stop the dancing and I could lock all those water molecules in place, that each OH group would have one frequency in the absorption spectrum. But I can tell you as a molecular spectroscopist, that's a rare bird. I mean, real spectroscopy usually has other junk in it that has to do with anharmonic coupling and line widths. And there's complexity here that is much richer than one oscillator or one frequency. So I'd like to know what the homogeneous line width is, and I'd like to know what that is at 0 Kelvin. So we're gonna address that as we go through this. And finally, when I've done it, when I've looked at a frozen chunk of water, I'll warm it up and see if I can reintroduce these fluctuations that lead to spectral diffusion. Well, if you're using relating to bulk water, because in a cluster, most of the molecules are on the surface. And so it's really it connects best with the spectroscopy of what's going on at the air-water interface. And we can get at that by using these nonlinear optical tricks where you have vibrational sum frequency generation started by Ron Shen. And so if you're at the surface, well, one of those hydrogens is poking out of the surface, 3,700 wave numbers. And so we can always recognize an oscillator that's just in free space. And then you have the bound waters, and even though it's at the surface, it has the same diffuse lump that water has. But now that because you have polarization tricks, you can use S or P polarizations in the three-way mixing. You can address different water molecules. So there are clearly different classes of water molecules with PPP configuration, 3,500 wave numbers, or you can come in with SPP and you will get, and I have something coming up on my screen that's plugged. There we go. It's the same diffuse featureless spectrum, more or less, a little bump at 3,200. So people talk about this. What is this? What are these waters that are at 3,500 wave numbers? I like this paper from Misha Mon, and they were doing ultra-fast experiments and isotope labeling and so on. And they're thinking that this 3,500 wave numbers absorption is a very special water molecule that's accepting a hydrogen bond, donating a hydrogen bond, and has its hydrogen pointing off into air, into vacuum. And so I want to know if we can experimentally determine the correlation between the two OH oscillators on the same water molecule when that molecule is embedded in a hydrogen bonded network. So that's the game. And the tools that I'm going to use to explore that are water cages. And so if you take 20 water molecules and you assemble them around a big ion like cesium, you can they naturally form these they're distorted pentagonal dodecahedra. So you have 12 5-membered rings. And then it's a pretty general phenomenon. So you can take hydronium, and this is what we're doing for DOE. We take hydronium and ask, how is it hydrated? How is a proton hydrated? The cesium goes to the center of the cage, and the hydronium is up here at the North Pole. So it floats to the surface, if you like, of one of these clusters, and a water molecule is inside the cage. So we're going to use these as a prototypical extended hydrogen bond network that has and ask whether it has anything to do with the interfacial spectrum of water. It's useful to point out that these reconstructions of water are quite general. And if you go to high pressure, bottom of the ocean, for example, put methane in water, well, methane doesn't want to make a hydrogen bond with water, and so water rearranges itself to form these pentagonal dodecahedra. And these, in real water, these go on forever. These are networked extended solids. If you go to cluster world and you put methane in water, that is not what you get. This is not a stable minimum at all. But if you put an ion in it, it is. And so you can recreate the object that looks like that methane in macroscopic water can be formed naturally if you assemble the water molecules with an ion. So this whole game was started by my colleague at Yale, John Fenn, when he, in a primitive apparatus, when he was developing electrospray. Of course, that's used ubiquitously for biomass spectrometry these days. And so he had water vapor and high voltage needle, and then took a spectrum. And on the x-axis is the number of water molecules. The y-axis is the intensity of the cluster that you make at each size. And it's clear that if you take hydronium and 20 water molecules, that's a very special, it's an intense mass peak. And intensity from the Gibbs free energy has to do with stability. So there's something especially stable about this assembly of 20 water molecules, and that's where it all started with thinking about these as these cage structures. Here's the cage. This is one of our mass spectra. If you grow water clusters around cesium, when you get to 20 water molecules, you can't miss it. It's a very intense peak in the mass spectrum, and of course we wanted to do more work on this with spectroscopy to see if we could get more structural clues about whether these cages are for real. Okay, so the big breakthrough, I'd say, in our work in this field was coupling the electrospray front end with a cryogenically liquid closed cycle helium refrigerator, a cryostat, in a radio frequency ion trap. And so we didn't invent that. That was a very lovely piece of instrumentation developed by Zubin and Lifeng Wang when they were at PNNL. And they showed that you could put ions in a Paul trap, a quadrupole trap, and effectively cool them down without RF heating. So once they're cooled down, then we inject them into a mass spectrometer. And so our mass spectrometer is a double focusing photofragmentation mass spectrometer. And so we intersect a pulse of ions that is drifting through the time of flight tube with a pulsed infrared laser, fragment it. We do tagging spectroscopy and get the infrared spectrum. This current incarnation of the experiment was made possible by instrument development grant, a DURIP grant from AFOSR. Okay, so does it have anything to do with water? So we showed you the SFG spectrum from Ron Shen. And this is the cesium water 20 cluster in red when it's at 120 Kelvin. And I claim that there are similarities to this. In particular, like, this little 3200 wave number blip seems to be hanging on. The shoulder looks the same. And this interesting 3500 wave number feature is very strong in the linear absorption spectrum. So I claim that even though it's a small object, it does have enough variation in local environment to span the range of infrared frequencies that we see in real interfacial water. Okay, the main trick that I'm going to use today is a gift from ion spectroscopists, mass spectrometry experts, and in particular, Einar Ugerud, a colleague of ours in Oslo. And he pointed out, we all thought that if you take D2O, one molecule of D2O, and you put it in a beaker of water, and you think you're going to follow the life and times of the D2O molecule, you can forget that because it's going to chemically exchange in sub-nanosecond time scale. You're not going to have a D2O survive. And Einar showed us that if you do this in small clusters, that's not true. So it means that you don't get chemical exchange, and that means that you can introduce an intact isotopically labeled water with both of the labels on the same oxygen. So it's a situation that's unique to the cluster world, and we're going to exploit that in order to figure out how to get these local pieces of information about the microscopic structure of water. Game plan to deconstruct these spectra, as it said in my title. We want to introduce a single intact H2O water molecule into the cage that's built from, we start with a cage of 20 heavy water molecules, and then we'll switch one out and put an H2O in there. If we're lucky, we'll distribute that isotope the isotopically labeled water among all the available sites, and it'll fill up the whole spectral region depending on which site it falls into. And here's the key. So we're going to figure out, if I just have one water and a bunch of heavy waters, well, they all weigh the same, and so it's distributed among every site. That won't help. But what I can do is use the fact that if they're stuck in a site, I can use an IR photo bleaching experiment in order to identify the spectrum that's unique to each site. So these are all isotopomers. They're distinguishable species because the label is in a particular site. And I can use bleaching to get the spectrum of a water molecule that's in that site. And so the game here is I want to know the correlation between the frequencies of the two OH groups on the same water, and I want to know how that depends on where it is. So let's grab one here. Grab a green water molecule. It's got symmetric. It's got the two OHs on it. I go over to the spectrum. If the ansatz is right, one OH, one transition, one frequency, there are two frequencies associated with that object. Now the problem here is that I can put the water all over the place. So it could be in a, it has a free OH poking out and so on. Each one of them will have a pair of frequencies associated with it. And if I just take a spectrum of an ensemble of ions and all I know is there's one H2O molecule in it, I'll just get a spectrum that's all jumbled. It has all of them overlapping each other. And so the trick we use is not some sophisticated coherent spectroscopy thing. This is a real boneheaded experiment, right? You just get yourself a powerful nanosecond infrared pulse laser and you blast away with it. And you find some feature in your spectrum, and we detected the spectrum, did we not, by tagging, by messenger tagging. It means that if I absorb a photon, I destroy the target. It loses its tag and it's gone from my experiment. And if I destroy the green water cluster, and then I ask what other feature in the spectrum goes away with it, the only thing that's going to go away is its companion OH. And so it's a bleaching experiment where I look at the correlation between the frequency that's tuned to the bleach, and then look for the other one that must be out there somewhere that is associated with the same isotopomer. And so we're going to do a bleaching experiment and isolate just these 2x2 correlations. And so we do that tactically in the laser part of the experiment. So we're going to probe on one of these transitions in a complicated spectrum, and I'm going to scan a bleaching laser earlier as the ions are drifting through in the time of flight apparatus. So this is blast and bleach, and then constantly probe. If I bleach and blow an ion away and I'm probing a feature of it, that's how I get a dip. Okay, so here's how the experiment works. I take a heavy water cluster, cesium, and this is the OD, this is experimental spectrum. This is the OD region, and it's cold. So you can see it's actually got a lot of well-defined features associated with this structure. And now I switch out one of the heavy waters and I put a light water in, and I claim it's an H2O. And what I look at now, I have action in the OH stretching region of the spectrum. And of course, if you're a graduate student, this isn't the happiest day of your life, because you realize that you got a cool experiment, but you just divided your signal by a factor of 20, because the water molecule is only one of them, and it's distributed among all these sites that it could fall into. One water molecule yields a whole slew of absorption lines, and it should only have two. So that means it must be the case that that water can fall into many different spectroscopically distinct places. And each one of them is overlapping, as I advertised in the cartoon of how the experiment works. So some of these are correlated with others, and I want to be able to pull out the correlation by using a bleaching experiment. Okay, so if we have a free OH, it's very easy to see it. 3,700 wave numbers, the only number you have to memorize for this lecture. And if I bleach that transition, somebody else is going to go away. Its buddy, the partner of that free OH, wherever they are, if there are many of them, all of them will go away, because I'm going to get rid of every single one of them that's got the property that one of its hydrogens is non-bonded. Let's bleach. So when I blow that away, I want to hunt. I want to hunt around in the spectrum to see where the companions lie. Thank you, Nan Yang, for those excellent graphics. So here's the result. So I bleach everybody who's got a free OH. I say, where's my other companion? They're all the lowest frequency members of the absorption spectrum. So, new rule, right? If you have the free OH, that has the property that it has the ability to push its companion OH farthest to the low frequency region. Which brings us to what is this thing? This is the 3,500 wave number band, and I can bleach this thing and say, well, where is its companion? Let's bleach it. So if I bleach one of these transitions, the other one's right next door to it, and moreover, they are separated by 100 wave numbers. Well, 100 wave numbers, that was the difference between the normal mode, symmetric and asymmetric stretch of an isolated water molecule in vacuum. And so all that's happened in this region of the spectrum is the water molecule is donating, both its OHs are donating hydrogen bonds. We call that an ADD water. And when it does that, they're equivalent. And so you get a redshift of each oscillator and they remain coupled. The reality of this coupling in a complicated environment like this if you can't think of a question, ask that one, because I think the issue of what this splitting really is due to is a fascinating one. Broad brush, free OH is the low end, gives you the low end region of the spectrum. And the question is, it's still diffuse. So is this just a homogeneous contribution to the spectrum, or is there substructure of the class of molecules that are AAD? This is the dodecahedron is formed with the free OHs are obtained by having two donors, two acceptors, and a donor. And so in order to separate out this region of the spectrum, I have to bleach within the diffuse junk and then probe around to see what's associated with it. Here's a bleach where I'm bleaching in this congested region of the spectrum. It's pretty cool. It reveals a pretty simple pattern that's embedded in it. Well, we knew it had a free OH, so that was a given. So it indeed, took away its companion is the free OH, but there's another sharp line in the spectrum, right? Two OH stretching groups, three lines. You can also see that it's fat. Some of them are fat, some of them are thin. There's a lot of information in these bleaching spectra. And so what is this? This turquoise feature here happens to fall almost exactly at the frequency of the V = 2 level, the overtone level of the water molecule's bending mode. So this is a famous thing that happens when you have an OH stretch that is proximal to the overtone of its bend. You get what's called a Fermi resonance. And so the way the game works is the Fermi resonance happens when you have a fundamental transition of the OH stretching region. Of course, the overtone of the bend in the harmonic oscillator limit, that's not allowed, so you won't see that. However, the bend and the stretch can couple with each other and make new quantum states that are mixtures of the two. And so people say that the bend gains oscillator strength through the coupling with the bright state, which is the OH stretch. And so here's the OH stretch. It's got this broad width. And we can see that the bend overtone's picking up a little bit of intensity because it's getting close to its OH stretch. The overtone's getting close to its OH stretch. And as I push the two levels closer together by increasing the redshift of the OH, look, it's getting bigger, right? You can get to a point where this is wildly mixed and then tune it so far that it comes out below the overtone of the stretch and the coupling goes away. And so from this analysis, we can deduce that the coupling matrix elements are on the order of 45 wave numbers for the embedded water's intrinsic intramolecular coupling due to a Fermi resonance between the stretch and bend. The dodecahedron was good to us with cesium, but it only gives you 2 of the 5 classes of water local environments that I advertised from that, the compendium, Martin Chaplin's compendium of what causes water to shift. I'd like to get the rest of them. And in order to get that, we have to break the cage. And so it turns out sodium does not like to make a pentagonal dodecahedron cage, and sodium ion breaks it. That was discovered by Evan Williams at Berkeley. And so we can find, using the sodium system, I can get access to what happens with this AD water molecule. One acceptor, one donor. It's very uniquely positioned in the spectrum, and I ask, where's its companion? Its companion is at 3,500 wave numbers. If it accepts 2 hydrogen bonds, it pushes it almost twice as far. So new rule, right? Accept a hydrogen bond, push a little bit to the red. Accept 2, double your money. And so we're developing this rule book for how much give and take you get for the local binding environment. It's kind of fun in that, at first I thought we had caught the ultrafast community, because remember Misha Bone's paper thought that it was this water molecule that was at 3,500 wave numbers. And if we have a free OH, like I just showed you, that only does that with an acceptor donor, it's exactly at 3,500 wave numbers. It really annoys me when these people get it right. And, we're not bringing truth with clusters to the table. But I think this assignment would work. I think that these in-plane water molecules that are the ADDs have much higher oscillator strength, though, when you're looking at that region of the spectrum. Okay, so we've talked about the embedded correlations in the water. I'd like to take on now the question of whether this is true that one OH group, one frequency. We have already seen that if I have H2O, I have an intramolecular coupling. I can get 3 frequencies, right, for an extra bend. And I'd also like to investigate this business of the line widths, because we could see that in the H2O spectrum, the bend was much sharper than the stretch one. And so what do we expect? If we say, what are we going to get for line widths? If I have a water molecule and it's in vacuum and I excite a vibration, what's its line width? Well, the line width is going to be determined by the radiative lifetime, the fluorescence lifetime. Really long for vibrational transitions, milliseconds, really, incredibly sharp lines. All right. If I put this same OH group in a hydrogen bonding network, well, it's embedded in a quantum system that has a gigantic density of states, because all of those low frequency bends and stretches and librations and so on, 3,500 wave numbers for an OH stretch launches you high into this very dense manifold of background states. And so this is the game of IVR, intramolecular vibrational redistribution. And so if there's interaction with that bath, then you're going to broaden out the oscillator strength, just like Fermi resonance. That was 2 by 2. Now you're going to have 1 by 10 to the 5 or something from this incredibly dense density of states, and it's going to broaden it out to look like a Lorentzian. So that's one limit you can imagine, that the intrinsic line width, even at 0 Kelvin, will be a direct measurement of the interaction strength. There's another thing that can happen. If I excite the OH stretching vibration and it's embedded in a medium, well, there are vibrational levels associated with the soft modes, the intramolecular librations and rotations. And I can excite transitions to them, and they will appear as combination bands in the spectrum. So there are many ways that this ansatz can be in trouble if you look in detail about the spectral signature of a single OH group. And so in order to investigate the properties of a single OH, we had to do an experiment to get rid of that Fermi interaction. So we wanted now to isolate only one, and that's easily done by just introducing a single HDO molecule. There's only one OH group in the whole thing. And we'll do another hole burning experiment, and we'll get the spectral signature of each OH group in each site. And again, I'm going to start with going back to this water 21 hydronium with 20 waters. And so we've worked on this for a long time, and I don't want to drag us through that for this talk today, but we think this is the structure of that thing. And this is the cold, cryogenically cooled infrared spectrum of it. Mike Duncan and I got this kind of thing going, it was 15 years ago now. And so this is the calculation from Sotiris Xanthias. And so you can start to see patterns that you can have the audacity to claim that particular waters in this cage are giving you particular transitions. Indeed, you can do pattern recognition in order to try to reconstruct whether you can understand the spectrum in terms of a candidate structure. So how can we push this a little harder to see if it's true? If I introduce only one OH, and that's why we did it in the first place, I want to get rid of all coupling, right? I want to get rid of intramolecular coupling. I want to get rid of the excitonic coupling between all the identical OH oscillators. Now it's only one OH, well isolated energetically from everything else in the problem. Here's that single OH that is distributed among 5 different spectroscopically distinct sites within this cage structure. And presumably there are a bunch of lines, because this is the calling card of the H, for example, when it happens to be in the free position. These won't be there if I had a way of just isolating that particular cluster with the frequency there, with the hydrogen there. So let's whole burn. So we walk through this spectrum, burning, burning, burning. And this is another case where it's like, boy, these guys really got it right. One oscillator, one frequency. The only place where we see an extra feature in the spectrum is down around 3,400 wave numbers, where we burned in one position, but got another transition about 100 wave numbers above it. So we think that this is the soft mode excitation that's happening in this particular frequency range. But for most of them, look at this triplet right here. Those are just 3 different sites that are giving 3 different local sharp frequencies. Now, again, we can see that as we go farther, as the bands shift farther to the red, the laser is very narrow. It's a 2 wave number laser vision, one of these OPOs. And this is a 100 wave number wide thing, right? So we're blowing out a lot of the spectral region of this cluster. And so it's useful to think about what's controlling the width of these lines. So Nan Yang has done a lovely experiment with many, many clusters, and this is a summary of them all, looking at the line widths as a function of redshift. And then if we plot that, it's an interesting case. So it's systematic. So I'm not making any claims about the detailed shape as Lorentzian or Gaussian. We fit them to Gaussians and got half widths, and then look for the trend and what's controlling this intrinsic frequency. And I was very surprised. I don't know what I was expecting, but it's above 100 wave numbers redshift. It's basically linear. And I want to emphasize here that the width I'm talking about is the width of an OH oscillator in a 10 Kelvin frozen cluster, right? There's no thermal motion here. This is like a 0 point effect, that we have an intrinsic coupling you can't get rid of that is revealing itself with this redshift. So that's a decoherence time, which is what's going to give you a width on the order of 100 femtoseconds when these things are very highly redshifted. I have no idea why that's true. And so we're kind of hoping to stimulate some theoretical work, because it's such a well-characterized system, in order to see if there's a simple way to understand fluctuations in fields or what's causing these intrinsic widths. Okay, so everything we did so far was we tried hard to freeze things down, stop the dance, and investigate the spectral consequences of the signatures of each type of water molecule embedded in a network. Let's heat them. Now that we know that, we're in a good position to heat them up and then start the dance again. And so when we do that, presumably we'll get to a point where we can cause water molecules, even in a cluster, to start undergoing large amplitude motions. And if they do that, we'll see frequency changes. So this is the 5-line pattern that we just talked about that is characteristic of this cage structure. And let's heat it up and see when the cage falls apart. 100 Kelvin. Pattern's the same to my eye. Broadening, I expect that. Starts to really degrade when you finally get to 150 Kelvin. 150 Kelvin is about the temperature at which the clusters evaporate on the time scale, on the millisecond time scale of our apparatus. So the cage is more or less intact at 100 Kelvin. They don't seem to be doing this, large amplitude liquid-like evolution in this range. If you start talking about thermodynamics and phase transitions in small particles, and especially clusters, it's a new and fun regime for statistical mechanics, thermodynamics. You go to liquid water, you go to 273, right? And you go to 274, it's liquid. And you can tell because in the caloric curve, you get a sharp break in the internal energy versus the temperature of the cluster, versus the temperature of the water. If you do it in clusters, there is no sharp break. It's not sharp. And it's much, much lower. The discontinuity in this heat capacity curve happens at almost half the melting energy of liquid water. So it's fundamentally different. And you can imagine that it's happening because most of the water molecules are on the surface when it's very small. So it isn't shocking that it's going to be different. And so you expect a diffuse sort of onset to what you would call melting in a bulk problem. This has been looked at with beautiful experiments from Bernd von Essendorf's group about 8 years ago, and they measured the caloric curve for these very same protonated water clusters. And they start to break off at about 130 Kelvin is when a water cluster starts to yield information that large amplitude motion is happening, phase space is starting to open up, and we can see it in the heat capacity curve. How can we see it spectroscopically? So if molecules are starting to move from one site to the other, and I claim I know that the frequencies associated with each site are a measurable reporter for where that particular oscillator is, then if I had a way of monitoring the frequency, if this oscillator had a radio and could call home, as it was 3,700, skipper, go 35, 33, back to 3,700. If I could follow the frequency of an oscillator, it would tell me whether or not it's doing large amplitude motion. That's the spectral diffusion that we were talking about in the analysis of the liquid water spectrum. So I'd like to follow the frequency of a single OH oscillator as a function of temperature and a function of time. Okay, so here's how the experiment works. The one thing that I show you these cages, but I want to really emphasize that what our experiments measure is an ensemble measurement. It's an ensemble that consists of 50,000 ions or so that are sitting in that ion trap. These are not single molecule, anything like that experiments. And so I'll always be remembering that I have a lot of ions that I'm talking to, and I'm looking at the property of the ensemble when I'm showing you spectra. So suppose I have a way of putting an OH oscillator in the free OH position, and it's undergoing large amplitude motion. So let's try that. Everybody else is a heavy water, and here he goes. So every time it moves around, it goes to a different frequency band, color-coded. We've color-coded our bands, and we're going to follow that migration of a single OH group. But remember, we're doing this with an ensemble of ions. So how do I get time dependence out of it? Here's an ensemble of ions, and all of that ensemble is just they're doing their ensemble dance. As I warm it up, they're minding their own business. They're isolated in a vacuum chamber. And suppose that at some unlucky point in time for these particular clusters, I tune my laser to destroy them. So they're gone. They're removed from the ensemble. And if I measure the spectrum of that ensemble, when they're gone, I will not find any absorptions at that free OH. However, if I just take the rest of them and they're all doing their dance now because they're warm, and I see, what do I see? I see that some of them accidentally have wandered back into being free OHs. The free OH will show a bleach and then a recovery. And the recovery time will tell me the intrinsic spontaneous time scale for frequency migration of a single oscillator among its available sites. So in order to do that experiment, Non and Sean Eadington developed this variation where we excite our infrared laser in the trap. And so we have to do that because the time scale for these spectral migrations, as you'll see, is really slow. So we can hold these ions in there for seconds. And then we subject them to our time of flight analysis in order to look at the absorption spectrum of the ensemble after it's had time, a dwell time after the bleach. So here's the sort of short story of how it goes. If I bleach at the free OH position and ask what's the absorption spectrum of the whole ensemble, it's only missing the free OH. This is a depletion signal. At 40 microseconds, nothing has happened. If I take exactly the same experiment, done exactly the same way, these are the same clusters, and I just look at them 50 milliseconds later in time, all of the absorptions are back. So they have spontaneously taken a situation where only the free OH was gone, and that free OH has now wandered to all positions available in the spectrum. Now, what's particularly interesting about this is the absorption spectrum of the ensemble at that point is the same as the absorption spectrum before I destroyed all the free OHs. It means that it statistically repopulated all the sites in that time scale. Means that the system behaves as an ergodic ensemble. So we can do real kinetics. This came out yesterday, by the way, in PNAS. So we can look at the bleach recovery. We bleach on the free OH transition, watch the recovery time, single exponential kinetics. And these are really slow. This was my, my attempt at humor in the titles. Slow but sure wins the race. Spectral diffusion in clusters, you don't need a femtosecond laser. These are glassy dynamics where we're looking at really slow, rare events. So it seems like we should be able to heat them up and get them to happen on a faster time scale. So let's do that. So let's bleach and look, 10 Kelvin, it's a stone, it's ice. 90 Kelvin, still ice, nothing's happened. 100 Kelvin is interesting. 100 Kelvin, I light up a little absorption way far away from the bleach site. Why are these two positions in the spectrum? It's jumping, it's blinking back and forth between these two frequencies. Why is it doing that? I claim it's because this water molecule is just rotating around. So the first fluctuation that happens is simple rotation of the water molecule. It's the free OH dives into its bound position. I already told you that the companion band of the AAD molecule is way down here at the low end of the region of the spectrum. Now, Francesco Paisani has looked at this very carefully using advanced, taking into account nuclear quantum effects and so on in small cluster sizes, and has seen how these dynamics can be treated with accurate, using accurate simulation methods. By the time we get to 110 Kelvin, all sites are starting to interchange, and I showed you 120 Kelvin before. It's game over. This thing is now completely acting like all oscillators go to all sites uniformly and statistically. Okay, so we've done a lot of work with, I would say, trick systems, isotopes, and tracking the spectral dynamics of water. And you might say, that's great, but now that you've done water, what are you going to do next? I claim that there's nothing special about doing these kinetics with spectral diffusion and isotopes. It's a completely generic experiment. As long as the spectrum changes, you can do kinetics. And the kinetics that we're currently looking at are when you have a molecule like this one where you can protonate it in two sites, on the amino group or on the acid group. And they both exist. We can detect both of them as different isomers. And so when you hydrate this thing, it is claimed that you can interconvert them through a Grotus mechanism on a water wire. And so now we're undertaking that experiment is happening this month at Yale, where we're going to try to expand the chemical scope of our methods. So what have we talked about? So we've seen the embedded correlation between the two OH oscillators on the same water molecule and how that varies with the site they occupy. We've seen, we've exposed intramolecular coupling that's a Fermi type resonance within one water molecule in itself. We've looked at, somehow my computer got into a bad zone there. There we go. We've seen the line width dependence that's linear, and I hope we can stimulate some theoretical work on that. And we have a new era opening up where we're looking at kinetics and ion traps using water clusters as little baby, as test tubes in order to look at the chemical kinetics on a molecular level. I've introduced you to the folks as we've gone through this, but I haven't given enough credit to Sotiris, Ken, and Ann, who have all been with us step for step as we've tried to work our way through the analysis of these cage dynamics and structures. So that's my story, and I'm happy to stick around and entertain questions.
That's great, Mark.
How did I do on time?
I think as we expected, you were perfect.
Go. I got that right.
Well, we'll talk to your wife if she agrees with that. So as we mentioned, Carlos and Rodrigo are going to moderate the questions. And I think Carlos is going to ask the first one, right, Carlos?
Yes. Okay, I just needed to unmute myself. So thank you, Mark, for the great seminar. There were quite a few questions in the chat, and I think they're still coming in. One of the questions that a graduate student asked is, after removing the bleach species, basically once you photo bleach your species, how can you expect that the spectrum of the rest of the cluster will remain the same?
You got to remember that when we bleach, we've removed all of the. I mean, you'd have to have a situation where the isotope was changing the structure, and we don't think in this class of cage. We have water clusters for which the D spectrum is totally different than the H, and therefore you might imagine that if you had the H in some position and you put it somewhere else, that somehow the spectrum will be different. But that's not the case in the pentagonal dodecahedron. So we think that when we remove one of these, one of these isotopomers, that the rest of the system is the same. It's the same it's the same scaffold that's holding it.
That makes sense. Thank you.
Go ahead, Rodrigo.
Thank you again, Professor Johnson, for such a great talk. This question comes from Nancy Levenger, and the question is about heating up the clusters and how that would affect the ability of the H2O and D2O exchange, or is it still really, really slow?
We don't see it. The experiments done in Norway were done at evaporation, in the evaporative limit, because they were doing them without a cryogenic spectrometer. And so the HD survival, works in the cluster world up to the temperature where they self-destruct by evaporation. Now, if you do that same experiment with protonated water clusters, it works with cesium. The alkali metals are the only ones you can do that with. If you work with a proton, then they're exchanging all the time. It's very difficult to shut it down. And a very talented ion spectroscopist at University of Wisconsin-Madison, Etienne Garand, has beautifully demonstrated how HD exchange starts to happen when you put water on a protonated peptide. So it really depends on whether you have an active proton or an acidic proton in the problem, whether you can see cluster world chemical exchange of the hydrogens.
Thank you.
Good question, Nancy, by the way.
Carlos, are you ready with your next one?
Yeah, there's a question from a student, I believe, that is asking, how can you attach an HOD molecule to the cluster? In other words, if you mix H2O with D2O, you're going to have a statistical mixture. So how do you know you're attaching an HOD molecule?
Yeah, that's the sort of, that's the loser's bracket, right? I mean, the D2O is the one that's hard to get. And so you do it, the way it works is you have, clusters or all D, you mass select it. I mean, you only have all D clusters, and then they fly through a vacuum chamber where you have a very dilute vapor of whatever the trace isotope you want to put in it is. And so, remember that these are mass selective experiments. And so if I just take water and shake it up with D2O, I have all the ice, they're all there. And most of them are HOD, right? 2-to-1. And so you just let them all hit, and then you mass select the one that happened to be the incorporation of HDO. So the mass spec does the work for you. It doesn't work when you want to do D2O because you could have picked up 2 HDOs and you can't tell the difference. So the D2O one, you have to have pure D2O in the vapor, the H2O in the vapor when you attack it with an all deuterium heavy water cluster.
Thank you.
The next question comes from Garrett Santos, and this question is about whether you would expect to have an upper limit on the linear region for the redshift versus bandwidth relationship.
I don't even know why it's like that at all anyway. So, we've seen, we saw it in those two very different systems, and so we published it saying, because we've seen this effect. Let me throw something out, maybe to stimulate some discussion on it. It's clear what causes an oscillator to redshift, right? A lot of people think it's the electric field, the local electric field is causing the redshift. And so you could imagine a width would come if you had a way of modulating that electric field. So if the electric field modulation was somehow proportional to the redshift, then that would be a mechanism for how you could induce this sort of coupling. But from my point of view, I don't know of any sort of, born kind of electrostatics way of looking at this that would predict linear in the first place. So, I have no idea why it's linear or when it would break down.
Thank you.
There's another question from Eric Bergay, related again to the HT isotope exchange and the temperature dependence. When does the exchange turn on with respect to either temperature or cluster size?
Yeah, I don't know how high we can go. I think Ugarud went into the, in the tens of clusters and showed it. We like to work with the smaller systems because you can actually, they're small enough you can calculate them, and yet they're big enough that they start to do interesting things. So yeah, at some point, okay, so why do we think it shuts down in the first place? Maybe that's the question. I don't know this stuff. I mean, I think that it happens because water's got a pH of 7. And so it's always got access to the dissociated ion pair state. But in order to get an ion pair, you got to have dielectric that'll solvate both of those, hydroxide and a hydronium. And so if you got a tiny cluster, you can't develop enough hydration to get charge separation. And so I would say if I need to develop, electrostatic stabilization in order to drive charge separation, I think that's a pretty big cluster. I mean, I'm not going to put a number on it on YouTube, but I think it's large.
Thank you.
Our next question comes from Sean Roberts, and first he said he mentions what a beautiful work you've been doing. So I wanted to mention that as well. And the question is regarding the spectral dynamics that you're observing would suggest that there's correlated motion between neighboring molecules in the cluster. And if there is a way to look at that explicitly, perhaps by playing games with multiple isotope labeled molecules in a cluster or by introducing tritiated water.
Tritiated water. Thank you for that excellent suggestion. That sounds like forms to fill out to me, but it's serious, and it's a good question. And I get that a lot. So I think another way to state it is, I think this is the question, can you use cluster techniques in order to not only talk about how one water molecule is coupling with the next water molecule, with it itself and why it changes its frequency, but how can you tell if you bring back the second water with an OH, 2 OH groups now, and look at how they talk to each other, like you might do in a 2DIR experiment, which is why Sean, I think, might ask such a question. And we think we can get at that by looking at the detailed spectral differences between the single H, spectra, and you have to look carefully because the effects are small. But if you look at how single H differs from the intact H2O, you can deduce what the coupling is to the nearby water molecules. And if we had a way to I don't have any magic wand that'll bring 2 H2Os of 20, and I can't sort out where they are relative to each other. I don't have any way to do that. But we think we have evidence of the coupling between water molecules by looking at the frequency shifts in old school spectroscopy kind of way.
Thank you.
There's another question related to the 0-point energy of H2O versus D2O. The question is, does that affect the spectrum or does that affect the exchange dynamics? Because, the bond length is going to be slightly different, the OH versus the OD bond length.
If you look at the 20 cages, the 20-mer cages, you can take the OH spectrum and divide it by the square root of 2, and you get the OD spectrum. So I don't think there's any funny business going on with nuclear quantum effects or 0-point energy in that class. We have an active program that is very aggressively looking at nuclear quantum effects in cluster systems for which that's not true. So if we look at protonated water hexamer, for example, and you look at all H and you look at all D, the spectra are totally different. The pattern's different. And so that's a case where the bond lengths are changing ever so slightly, and the isomer possibilities are so close together that the isotope, you change isotopes, you get a different structure. But the 20-mer is robust, so I don't think it's susceptible to that effect.
Thank you.
Okay, so I just want to jump in and say, I'm sure, Mark, you've probably been paying attention to your talk because it was that good. We've gotten some amazing questions. Rodrigo and Carlos have picked their 2 favorite remaining questions, and they're going to ask those 2, and that'll be it for the main session if we can all agree on that. All right?
Well, everybody's got my email address, so if I piqued your interest, I'm certainly happy to grab a cocktail and muse.
We can dream about the days when we can all share a cocktail at a meeting. So Rodrigo, I think you have your good final question, right?
Yes, I'm good to go. This next question, last question, comes from Jack Sage. And the question is, DTO does not exchange in H2O cluster, but any interest in seeing when it does exchange when raising the cluster temperature and getting kinetics like you did with vibrational redistribution?
I think a question came up earlier, and I think here's what I think. Water's a bad choice if you want to look at HD exchange, because you have to change the ion in order to give it a different template, and then you can start to work with more active protons. So we have a very active, maybe the related question is, we're looking at, with Shayoni Mitra in my group, we're looking at, if you take nitric acid and you put it into 20 mer and ask when does nitric acid dissociate, it's easy to see dissociation of nitric acid, and it occurs spontaneously at 10 Kelvin when you have 10 water molecules around it. And then it reassembles by the time you put you fill up the cage to 20. So that tracking the active sort of, chemical activity of protons of acids is something that's nice to see, and we're working on that aggressively. I'm not so optimistic that we're going to get there with pure water.
Thank you.
Okay, and the final question comes from a student, actually, who is used to thinking about photo bleaching in terms of a molecule photo bleaching and never coming back from a context of, for example, single molecule microscopy. So the student asked if you could comment a little bit more on the terminology photo bleaching that you're using in your talk.
I guess I'm looking at it from the point of view, if I didn't know anything about what I was looking at, and all I did was have I had a method to measure the spectra. It's a black box. And so if I do something with another, if I intercept the objects that are in that box, and I knock out frequencies and I scan the spectrum again, I will see holes in that absorption spectrum. And in that sense, I think it makes intuitive sense to me to use the language that it's been bleached, because there are absorptions that have been removed by the action of another laser that's interrogating the system.
Okay, thank you.
Okay, Anne, do you want to have a couple final words?
You're muted.
You're muted. So we're reading your lips at this juncture.
I realized I was muted after I started talking. Someone had to do that, otherwise it wouldn't be a proper Zoom session. So I wanted to thank Mark for an absolutely wonderful talk and really getting this program off to a great start. Our next speaker will be Sharon Hammer-Schiffer, and I believe, Christy, you can correct me if I'm incorrect. People, even though they're registered for this one, will need to separately register for that one.
And I think it should be possible for us to send out another announcement by email. Mm-hmm. Through the Phys division thing. So we will take care of that on our end. And we have some notes about things that maybe next time we can do a little bit better, but I think it went super well. And with that, maybe we can all
I have one more little thing to announce. Sorry. For those who are interested, the Astrochem division has a separate seminar program, and their next speaker is on Wednesday of next week. And I would check the Phys webpage for links on that one. But there are two different series, and we're both monthly. And next month, as I said, Sharon, and she's starting 30 minutes earlier. So hers will be at noon Pacific, 3 p.m. Eastern, just to avoid that confusion as well.
Correct.
So thank you, everyone, and especially Christy and Carlos and Rodrigo, and particularly Mark Johnson. And I believe at this stage, we will remain open for the students and postdocs.
Right.
And
everybody who's a professor or in the energy industry, it has a permanent job, get out of here. Professor Johnson will be able to take some questions. And I think while this was going on, I have a way that if we can get rid of all the faculty and make it just the students, if you want to start putting your questions in the chat, I think I've figured out a way that I can make it so we can select you and you can ask your question directly to Professor Johnson, if that works.